As you already understand, Israel is involved in diverse space projects, and the next one is no exception. The European Space Agency's JUICE mission to Jupiter is planned to launch in April 2023, and it will carry a measurement system developed in Israel. To tell us about the development challenges of this measurement system and the planning of the experiment that will use this system, I'm delighted to invite to the stage Dr. Eli Galanti, a scientist at the Weizmann Institute, and Mr. Roniman, a project manager at AccuBeat.
Right, thank you very much. Good morning, everybody. It's great to be here. Wait till the end and then you'll see if it's worth clapping. I'd like to tell you about a really exciting adventure that me and Ronnie are sharing, which is an adventure that started in Israel with designing and building a really unique instrument, designing an experiment that will reach all the way to Jupiter, and I hope will tell us a lot more about this great planet. This is a joint cooperation between us, the Weizmann Institutes, AccuBeat. We designed the experiment, and AccuBeat who joined and built a really new design of an instrument that was never seen before. And all of that was funded substantially, a substantial funding from the Israeli Space Agency, without which we would never be able to do something like that. Okay, so a little bit of scientific background. Oh, I see that everything is together. Here's Jupiter on top left, is part of the giant planets, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. And to scale, I put here also Earth, so you can see the relative sizes of Jupiter to Earth. You can put comfortably about 1,000 Earths inside Jupiter. Okay? Jupiter is a gas planet, but don't be fooled by the name gas. It's not a fluffy gas, maybe on the outside in the clouds that you see here, but inside it's a very dense and complex matter that get to about maybe 10 to 20,000 degrees of Celsius and pressures that are unbelievable high. Jupiter is really exciting, and starting from Voyager, I see, oh, we don't see the animation. Okay. All right. You'll have to imagine that Voyager at 1979 flew by Jupiter and showed us that those tribes that we see here on Jupiter high, they are moving really fast. There are very strong winds on Jupiter, very interesting dynamics that is organized in those stripes, east-west stripes. And this is the interest that we have in Jupiter. We study the dynamics in Jupiter, and we are already involved in a NASA mission, Juno, that is orbiting Jupiter for the past 6 years. We were able to discover, using Juno to gravity measurements, that those winds at the surface, they penetrate about 3,000 kilometers inside the planet. 3,000 kilometers. So very deep winds, very interesting dynamics. But we wanted to do more than that. And the thing that we want to get is really a 3D map of the atmosphere of Jupiter. Okay? Get the composition, the density, the temperature, the pressure at the outside of Jupiter, but get a 3D map, not just a single experiment. And the way to probe the Jupiter without sending a probe, which is impractical, is to do the following experiment. This is called radio occultation. You have the spacecraft transmitting a very stable frequency to Earth, and while it's outside of Jupiter, then we know what it should be. There is a Doppler shift of this frequency, because Earth is moving and the spacecraft is moving. But then there is this special time that the spacecraft starts to go beyond Jupiter with respect to Earth, where we watch it. Once that happens, then you have a breaking of this transmitted wave. You can see this in the lower line. And this breaking is as a result of the composition, temperature, pressure of the atmosphere. This is where our experiment is going to be. We're going to understand this breaking of the wave, and from that we get information about the structure of the atmosphere. But to do that, you need to have an ultra stable oscillator, because the frequency has to be stable completely for about 1,000 seconds, 15 minutes. This is the time of the experiment until we lose the signal. And to do that, we need to really needed to build a new instrument, and this is where AccuBeat came into play. So Ronnie will tell you more about that. And our opportunity came with the JUICE mission. That's a European Space Agency mission to Jupiter. It's a big spacecraft. I'll tell you a little bit about it in a second. That will enable us to get about 130 occultation experiments with a very nice latitudinal and longitudinal spread. So we will get really, for the first time, a 3D map of the atmosphere of Jupiter. I won't go into the details, but doing that experiment will tell us more about the inside of Jupiter. And believe me, understanding Jupiter is understanding the solar system. This is the largest planet in the solar system. Understanding how it was created, how it evolved, will tell us also about our own Earth and how it was formed and evolved in time. So about the JUICE mission, it's European Space Agency mission. It was going to be launched. This is why it's very exciting for us. This April is the launch from French Guiana. And it will reach Jupiter at July 2031. Okay, imagine that. You need to be patient for a long time. And then it will orbit Jupiter and the satellites, big Galilean satellites of Jupiter for 4 years. In a few words, this is a huge spacecraft. It's about 5 tons heavy, okay? Really big one, powered by sonar panels. It has 10 instruments. On the left, you see all the instruments that do remote sensing, visible, infrared, ultraviolet, sub-millimeter radar for the moons. And on the right, you see other instruments, some particle instruments. There's the magnetometer, and then here's our instrument, the 3GM. This is a combination of 2 instruments. One of them is our Ultra Stable Oscillator. Our instrument will sit inside the vault of the spacecraft. It doesn't need to be outside because its functioning is to generate a very stable frequency that will be transmitted with the Eigen antenna, which is on the back of the spacecraft. A little bit about how you get to Jupiter. So it's a little different than sending a satellite to orbit Earth, right? Because when you want to go to Jupiter, you need to have a really high velocity to be able to get there in a reasonable time. And to do that, look at this orbit and that JUICE is going to do. It's going to be launched this April 2023. After 1 year, it will come back to Earth and do a lunar Earth orbit, get gravity assist from Earth. It will go away, get to Venus, get another gravity assist, like a slingshot, get back to Earth, 2026, go away, come back to Earth again for the third time in 2029. So in 2029, we'll get JUICE coming back to Earth, and only then it will go to Jupiter with the proper velocity that will enable it to get in a reasonable time to Jupiter. And then it will do an orbit of about, it will orbit Jupiter and the Galilean satellites for 4 years. This is when we will do our experiment. So I'll finish here and I'll get Ronnie continue with the development of the USO.
Thanks, Eli. Well, date is July 2013. Location is Rome University. Professor Luciano Yes, the PI, the principal investigator for the JUICE 3GM, is calling Yochai Kaspi, Professor Yochai Kaspi from Weizmann Institute. Yochai, would you please call AccuBeat and check if they can make a USO for our project? Sounds good. Yeah? Okay. So Yochai Kaspi, he was not aware of AccuBeat, but he called AccuBeat in Jerusalem, and that was the story how we joined this project. AccuBeat is specialized in developing and manufacturing of accurate time and frequency systems and atomic clocks for space, military, commercial application, which combine high performance in a harsh environment conditions and advanced technology. AccuBeat is already doing that for 30 years almost. I think next year it will be 30 years. and we are in the communication, SIGINT, C4I navigation, radar, spoofing detection, and space. Also, AccuBeat atomic clocks. Sorry. AccuBeat atomic clocks are actually part of the ground segment of the Galileo GNSS, the GPS, the European GPS, not in the space, in the ground. The first product in the space will be actually what I will just describe. So Eli talked about the spacecraft. Just take a look and see how does it look in compared to people on the ground. It's a huge one. And you can see on the right side, on the small side, you can see the Ultra Stable Oscillator located in the spacecraft. Okay, this is the Ultra Stable Oscillator, just some introduction. You can see the dimensions. The height is 10.5 and it's 16.5 by 12.5. Whoever went through our booth yesterday could see it and feel it. The main purpose of this instrument is to provide very stable frequency, as Eli explained, and the stability should be 5e to the minus 13 between 1 to 1,000 seconds, and under operational temperatures of minus 20 to 50 external temperature. It weighed less than 2 kilo. And the whole project was funded by the Israeli Space Agency. We are now at TRL 8. That means that we are ready for launch. This is the level of program readiness. We achieved the stability of 5e to the minus 13. I'll show you that in a minute at 1 to 1,000 seconds. We comply with JUICE environmental requirements. JUICE environmental requirements is very demanding. The magnetic field around Jupiter and Ganymede are crazy, are the highest in the planet that we know. So that means that we have to comply with higher radiation environment of the TID, total ionized dose, should be 50 kilorad. That's hard for the space components. So we made the qualification for this harsh environment. Here you can see we had to build in-house testing vacuum chamber, thermal vacuum chamber, that is very accurate, can control minus 20 to actually plus 70 C, because we had to test for minus 20 to plus 50 with a low pressure vacuum, at a vacuum pressure of minimum e to the minus 5, but we get lower than that. And the reason is that because the tests that we have to run every time are very long, and the stabilization go very slow, and it takes about 45 days for each test. So we had to have it at home, not mentioning that we need to have a very, very good reference in order to be able to test for this level of frequency stability. We had a management challenge here, and this was the first time that we worked with ESA from the beginning to the end of the project. A very, very tight work with ESA, with the Israeli Space Agency, and with the Italian Space Agency. They were all new for us. The Spacecraft Prime, Airbus Defense and Space also, were in very intense relations, so that's another demanding environment. And the Academy, Rome University and Weizmann Institute, so that was a challenge. Documentation, there is a joke running in ESA. If the weight of the spacecraft is 5 tons, then the documentation is 15 tons. And that's true, okay? At least our documentation. So that was very demanding. And COVID-19 started exactly when we started to build the flight model. And that was actually terrifying environment to work, but we were able to provide it on time when it was defined, in order to start the test of the spacecraft itself. So I can show you a few tests that we ran on the USO. The testing was done in few sites. We can see here now tests that were done in the European Space Agency location in Estek. It's in Netherlands. You can see here magnetic sensitivity on the left, up left. In the bottom left, you can see micro vibration. That means that it tests how the USO, Ultra Stable Oscillator, is behave under small vibrations when the solar wings are moving. On the right side, you can see in the bottom EMC testing. On the upper picture is performance testing. This is a vacuum tank, and you can see the USO inside. We performed tests in AccuBeat, and we performed the vibration and shock test in Rafael in Gusegev. We delivered 2 engineering models, 1 qualification model that we made qualification on, 1 flight model, it's PFM called, it's proto-flight model to those who are familiar with, and it was delivered on January 2021 and was integrated into the spacecraft at that time, and then flight spare almost a year later, and that's because of the COVID-19, most of this delay. Here you can see actually the results, and this is interesting to see because what you see here is on the x-axis you can see this is a time up to 10,000 seconds. On the y-axis you can see the stability, and as long as the numbers are low, it's better stability. Okay, and you can see the specification was 5e to the minus 13. And actually, on some of the range, we achieved 10 to the minus 14 results. And here below, we can see what Professor Caspi wrote, that in his opinion, this is the best stable USO in the world for deep space. And I got, by the way, the same comments from NASA, so I believe it now. So we are very proud of this. Here we can see...
Ronnie, let me just say, Ronnie is being modest. There's only one other company in the world that can do something like that. And the fact that a relatively small Israeli company was able to reach this kind of precision is really worldwide, will give them worldwide recognition. This is a really big achievement.
Thanks. Thank you. Actually, NASA contacted us for another mission. It's like a science fiction mission, and they're expert on. I'm saying that because Eli already talked about it. They're expert on time and frequency. Told me that if the results would not be signed by ESA, you wouldn't believe it because it's on the edge of the physical option at all. So here we are on the Twitter, ESA Twitter. You can see the team on the right upper picture, and they write that the 3 GM experiment with the state-of-the-art clock is now capable, complete and integrated into the spacecraft. And they thank AccuBeat and the 3 agencies and Rome University and Weizmann for their tireless dedication. It was really a crazy project. And here we can see another thanks we got from ESA. ESA and Airbus would like to thank AccuBeat, etc., for the results of the 2 USO units with excellent performance. The project was ended, but we wanted to use it for education for kids in Israel. And we announced on a picture competition up to age of 12. We got about 400 pictures, and we made a calendar. I don't know who of you visited us in the booth yesterday could get it. In the bottom of each month there is a question, and it's progressive. The questions are actually teaching you about time, clock, atomic clock, cyber, GPS, and quantum, and you have to scan the QR. You get this screen on your cellular, you choose the months, and you get the answer. It's including links for videos, etc. So thank you for listening. And now the only thing we need to do now is to launch JUICE. Please go ahead. I'll tell you something when you see it. You see the picture above, right? This picture actually, the idea of picture competition was not mine, it was ISA. They made it for the whole world, and that was about more than 2 years ago. And a Ukrainian girl, 8 years old, is the winner, and they paint her picture on the top of the rocket. By the way, the animation was done especially for this conference. I've asked them last week to do it, and they did it for us. The music, by the way, was added by my son. They didn't have enough time to put music in. Actually, I don't understand why they have to spend €1.5 million when they can do animation.
This is, by the way, the high-gain antenna that will deliver the USO signal. You cannot see the USO, as I said, because it's inside the vault. So it doesn't need to be outside. And the other thing that you will not see is how the sonar parlors are opening, but they are huge, huge panels on both sides.
85 square meter area. We wish a successful launch in April in Kourou. Thank you.
Thank you very much.
Thank you very much, Dr. Gallant and Mr. Mann, for this enlightening talk.